The topic of my discussion today is a case study on refrigeration requirements during mineshaft excavation as a function of heat stress index. On our agenda today, I'm going to introduce the topic. I'm going to go through the background, which serves as the main motivation behind the present work. In order to frame this study, I need to introduce two variables, one of which is the cooling power surplus, or CPS, the natural version of the wet bulb globe temperature, or WBGT sub n. I'm going to walk us through the problem, going over the schematic, design criteria, and simulation inputs. I will then briefly go over some of the results that were obtained from this study. There's going to be one on the baseline scenario, a couple based on the natural wet bulb globe temperature, and then an energy balance on each one of those scenarios. And then I'm going to conclude the presentation with a few closing remarks. So whenever people are working at depth, they're always going to be confronted with two inescapable heat sources. That's going to be autocompression as well as static heat. And today, a lot of mining companies are continually going deeper to extract the ore. And this has the tendency to subject their workers to potentially high levels of heat stress. And according to NIOSH's definition of the term, heat stress is defined as the heat load that an individual experiences from the combined effect of environmental and physiological factors, which translates into additional heat storage within the body. In order to quantify this level of heat stress, the workplace is mandated to have in place what's known as the heat stress index, which is a single number that allows them to assess the level of compliance with in-place legislations on heat. What we have at the bottom on this slide is it shows the several categories of heat stress indices from least to most complex. At the very bottom, we've got direct indices, which includes the wet bulb and dry bulb temperature. Moving up, we've got empirical rational versions. Probably the most well-known is the wet bulb globe temperature. And then we move up to the most complex, the physiological indices, which requires monitoring of human performance. So the subject of heat stress indices is kind of difficult. In industry, there's no universal agreement on which one is best. And the reason for this is, in order for it to be considered universal, an index must satisfy these four constraints. They have to be both accurate and feasible. They must account for both environmental and physiological indicators of heat stress. If it requires any calculations or measurements, they have to be easy to perform, as well as the indices exposure limits must function under a wide range of metabolic and environmental conditions. It's not to say that there hasn't been a lot of research. There has been a lot of research into this field. It's just that the common theme behind all of the previous works is that they fail to address the practical ramifications on the category of heat stress towards engineering controls. So this kind of ties into the motivation behind my work. And what I wanted to try to achieve in this study were three things. Number one, I wanted to analyze the refrigeration and airflow requirements, specifically during shaft excavation using our software, Vensim Design. Number two, I wanted to investigate the concept of cooling power surplus while working with the wet bulb temperature. And lastly, I was interested in seeing how the empirical heat stress index, the natural version of the wet bulb globe temperature, how it influences the ventilation and cooling design that was initially conducted utilizing the wet bulb temperature. So moving on to the methodology. The first variable that I want to talk about is the CPS, or cooling power surplus. By definition, it simply means the air's current ability to absorb a certain amount of heat before the air temperature equates to a design wet bulb temperature. Mathematically, it's pretty simple. It's simply the mass flow of air times the difference in sigma heat, where the reject temperature, or the reject version of the sigma heat, is the target wet bulb. And we can see that the sigma heat is purely a function of wet bulb temperature. To kind of help visualize this concept, on the right-hand side of the slide shows the top part of the model. Upstream of the chiller, the snowflake icon, the air has a CPS of approximately 1.4 megawatts. And what that simply means is at that current location, this parcel of air will be able to absorb 1.4 megawatts of heat before its wet bulb temperature arrives at the target wet bulb temperature. And then just following downstream of the chiller adds an additional 1.4 megawatts of cooling power. So it enhances its ability to absorb heat. The second variable that I want to talk about is the natural version of the wet bulb globe temperature. The main criticism of the standard version of wet bulb globe temperature is that it is rather insensitive to changes in air velocity. So to kind of address this deficiency, I incorporated a correction factor to the standard equation of the wet bulb globe temperature. And all that is I've introduced into that equation what's known as the natural wet bulb temperature. And all that is it's a correction factor to the psychrometric version of wet bulb based on those three regimes. So how we interpret this is when the air velocity exceeds 3 meters per second, the natural wet bulb temperature reverts back to the psychrometric version, and then we arrive at the standard form of the wet bulb globe temperature. So now I'll go over the problem. What we have on this slide is a schematic of the model. On the intake side, we have a dual stage intake fan, which supplies untreated fresh air through a chiller down a long duct column. The duct column begins at 1.37 meters in diameter, and then it narrows slightly as it arrives to the cutting machine. The cutting machine has several work and service decks, and what is interesting to note is that this duct column is uninsulated. So within Vensim design, when you construct the duct, you usually have an option to select or deselect heat transfer. In this case, that was turned on. On the exhaust side, we've got a single stage exhaust fan, which discharges both a combination or a mixture of untreated fresh air and the return air that's coming up the shaft. On the inset shows the 9 specific airways that were analyzed, and all its detailing is for each one of those airways, it's showing either a cooling source or the heat sources that were applied to those airways. On this graph, we see a trend of productivity loss as a function of wet bulb temperature. This graph was derived from Australian coal mines, and it has been adapted here to give us kind of an indication of what sort of exposure limit should be used for the wet bulb temperature. And just to give out a number, at approximately 28 degrees wet bulb, this would translate into a productivity of 87.5%. And in an 8-hour shift, that just means that a person works for 7 hours. This slide shows the main design criteria as well as the simulation inputs. It contains all of the important factors. What's important to note here are the limiting wet bulb, dry bulb temperatures and the exposure limit for the natural wet bulb globe temperature. Okay, so moving on to the results, this slide shows a summary of the baseline scenario of the 9 airways in question. What's important to note here is when looking at the inlet conditions for wet bulb, the picture that's being painted is actually quite favorable. With the exception of just one airway, most of the airways are in compliance with the wet bulb temperature. However, because of the the way the heat sources were applied, there was a predominant use of dry or sensible heat. And what this causes is actually a large wet bulb depression. And what that is it's just the temperature difference between your wet bulb and dry bulb temperatures. While if we then focus our attention to the CPS column, we actually see that this variable is decreasing monotonically, and that kind of makes sense as the return air is moving, traveling back up the shaft. It encounters one additional heat source, and those heat sources is essentially bringing the temperature, the wet bulb temperature, closer and closer to the target value. When you focus your attention to the pie chart, which shows the percentage of heat to the various heat sources, our options here to actually de-escalate heat stress is rather limited. We can either enhance the ventilation, add cooling, or a combination of the two. And the last thing to take note of is we can see that there are several airways at the inlet while looking at the wet bulb, the natural wet bulb globe temperature, that are not in compliance. So in the next slide, we'll show additional scenarios that will try to comply with the natural wet bulb globe temperature. So on this slide, we've got 3 additional scenarios. Number 1 was to increase the fresh air intake from 30 to 38 cubes. The second try was to take option 1 and then add an additional chiller at mid-shaft. And then the last option was to have a look at option 1 plus additional water cooling on the cutter, which would effectively reduce the heat dissipated from the equipment. And what we see on the graph on the right-hand side, both options 2 and 3 offer a similar level of temperature reduction, with the exception that option 3, the peak natural wet bulb globe temperature slightly exceeds the exposure limit. Okay, on this slide, we've got a bar chart showcasing the energy balance for all 4 scenarios. And how we interpret this is the black and white bar chart is just the summation of the heat sources. The one in red is CPS, and the one in blue is refrigeration quantity. The way the CPS in this study, how it was calculated was I observed it from surface, and then I prorate it based on the expected leakage. Ideally, the refrigeration quantity based on the wet bulb temperature should simply be the combination of heat sources minus the CPS. What was interesting to note is that because duct and strata heat was included, that has a tendency to make the energy accounting balance non-trivial. And the last thing to note here is that the larger the overlap between CPS and refrigeration quantity, all that just means is that the natural wet bulb globe temperature will be lower for each case. So in conclusion, for this specific case, the work reported the following. The first thing is baseline results informed by the wet bulb temperature predicted a mostly favorable thermal environment. Number 2 is that the advantage of using the wet bulb temperature for heat stress compliance is that it facilitates the energy balance calculation through the CPS. And consequently, the predicted refrigeration quantity is derived by subtracting the sum of the heat sources, or rather subtracting the CPS from the known heat sources. The third is solutions driven by natural wet bulb globe temperature compliance required either enhanced ventilation and cooling rates, or increased ventilation plus a retrofit on the cutting equipment. The last thing is, suppose a mine were to have a similar profile of heat, meaning a greater percentage of sensible heat to latent heat, might be confronted with a choice of either utilizing the wet bulb temperature or the natural wet bulb globe temperature. My advice here is for the design phase, use the natural wet bulb globe temperature because it does offer a margin of safety. But while, let's say in this case, for during shaft excavation, to expedite the work and for just monitoring levels of heat stress, go with the wet bulb temperature. Thank you, and I welcome any questions at this time.
Thank you, Kevin. Who has our first question? Thank you, Michael.
Very good presentation. Really enjoyed that. There's another gentleman that I think most people here would know, Rick Brake out of Australia, that came up with something very similar, but it added one more element. He called it thermal work limit. It took in velocity as an example, but the other factor that was that he added to that was really PPE, the protection. What the people are wearing underground as an example, and I think that's a pretty valid thing to add to that. And especially if they're working at the heading as an example, maybe not on the main shaftway, but how you measure that in the headings where the people are.
Yeah.
So have you seen any of his work, Rick?
I have actually seen his work on the TWL. The way it was derived is definitely not straightforward. He put a lot of work into that. So I am familiar with the thermal work limit. I think Ventum Design does incorporate that as another heat stress index. But in terms of this particular work, it's treated separately or differently from his.
Thank you.
Thanks for the presentation. That was really good.
Thank you.
The wet bulb and WBGT, it comes up all the time in North America. ACGIH, that's the heat stress index, wet bulb, globe temperature.
Yeah.
This is more of a comment. When selecting these systems, I have personally found it difficult to interact with clients talking about WBGT, that's a heat stress index.
Yeah.
And then the wet bulb, it's not a heat stress index in North America, but it is in South Africa. But that gives you the energy of the air.
Yeah.
Essentially,
Yes.
a dry bulb is a very, very small component of the energy of that air.
That's correct.
And so in South Africa, it was really easy to have those conversations. What are we designing to? It's the same number for your refrigeration system as it is for people underground. Because the WBGT, you can have, if you choose a number, 27.5 or whatever the number is, you can have many wet bulbs within that 0.7, that's 70%. What is your comment on the work you've done, or can you comment on choosing an appropriate wet bulb to represent the WBGT?
Yeah, that's a good point. You are right. You can have a definitely high spread of wet bulb globe temperatures. So you may have seen in the presentation a way to kind of narrow that range is to those mines that are specifically operating with the wet bulb in mind. They will also introduce that additional factor. Make sure that the dry bulb does not exceed a certain value. So that kind of helps narrow the range that can be observed. But it's still problematic though. So that's why, to kind of avoid that double treatment, just use a single heat stress index, which is the wet bulb globe temperature, or in this case, the natural version.
I wish everyone would just do that, but they don't. One other comment while I have the mic is grouping the terms. You had auto compression as a heat source. I find it beneficial to group auto compression with, in South Africa, they call it natural air cooling. You've called it CPS because it's a function of flow rate.
Yeah.
So there is a sensitivity. The more air you send, you have more natural air cooling, but you also have more auto compression.
Yeah. So you are correct. The reason why I lumped it into the heat source is that the way I treated the CPS in this problem, I looked at it directly on surface, and then I kind of prorated that or reduced the CPS as as a function of the expected leakage. Yeah.
Okay, any other questions? No? All right, thanks a lot, Kevin.